We're going to go ahead and talk about lesson 3.7, 3.8 all together in one lesson, and it's about graphing rational functions. So a rational function is a function with a polynomial expression in both the numerator and denominator. The expression in the denominator must be of degree 1 or higher. So, for example, we're going to be looking at functions like f of x equals maybe x squared minus 4x minus 6 over x minus 5, something like that. That has a polynomial in the numerator and a polynomial in the denominator. All right, so our strategy for graphing these rational functions. We'll talk through a few things. I might write a couple of things down to help you out. And then the next videos will be specific examples of actually graphing some rational functions using these strategies. So first of all, factor the numerator and denominator as necessary. Sometimes it might be factored already, but sometimes it might not. So you might have to use some of these things that are mentioned here, factoring out a common factor, using the quadratic idea, like factor a quadratic or something that's quadratic-like. So that's just kind of like this numerator up here, that's a quadratic one. Factoring by grouping sometimes can be used if it is x cubed function. Factoring using the rational root theorem and synthetic division might have to be used once in a while, and sometimes, not very often, but sometimes we might have to use the quadratic formula. So we're going to factor the numerator and denominator. Next, once it is factored, you could have holes in the graph, and we haven't seen that before, but what that is, like if we had a hole in a line, so here's a line, and if we had a hole there, that would just be a part of the domain is not there. So you're missing a part of the domain, like maybe if this was 3. So we'll take a look at that, but that's if you have canceled factors. That would be, for example, if you had g of x and we had factored and we got something like x minus 5 times x minus 9 times x plus 4 over x plus 3 times x minus 9. If you had something like this, these actually cancel. You will have a hole at x equals 9. So you would have a hole there because the 9 doesn't really affect the function anymore once it's canceled, except that in the original function, having 9 would make the denominator 0, and you cannot divide by 0. So that would have a hole in the graph. And as we go through graphing these later in the examples, we're gonna write these things. We're gonna write holes, and then we're gonna write zeros or x-intercepts, and we're gonna write vertical asymptotes, and we're gonna write horizontal or slant asymptotes. And each time we're gonna work through and talk about, so horizontal or slant, they kind of go together, asymptotes. And for each function, we will walk through each one of those 4 things. So continuing to number 3 here, it says values of that make the numerator equal 0 are zeros or x-intercepts. So that's what I was mentioning here of the function. Now this is very similar to when we graphed polynomial functions. We would find zeros of the graph of the function. And if the factors were odd multiplicity, it will pass through the x-axis. If it's even multiplicity, it will bounce off or change direction there on the x-axis. And the reason this holds true is because when you have a fraction, when does this fraction equal 0? Well, a fraction is equal to 0 when the numerator is equal to 0. That's why we check the numerator. A fraction's equal to 0 only if the numerator is equal to 0. So that's how we find x-intercepts or zeros. Then we're going to look at vertical asymptotes. So values that make the denominator equal 0 are vertical asymptotes. Something similar with the multiplicity. If it's odd multiplicity, the vertical asymptotes will go, or the graph will go in opposite directions on either side of the vertical asymptote. If it has even multiplicity, they'll be on the same side as the x-axis on each side of the vertical asymptote. The reason we use the denominator, so let's look at maybe j of x. When's a fraction undefined? That's when we have vertical asymptotes. Well, that's when the denominator is equal to 0. I do really want to point out a couple things here. So this first one, if you have what this looks like, if you have a graph and maybe we have some vertical asymptotes here. If it's odd multiplicity, the graph might go down closer and closer to the vertical asymptote on the left side of the asymptote, and so if it's odd multiplicity, it would have to go up on the other side. They have to be in opposite directions. Whereas if you have even multiplicity, and there's an asymptote here, if on the left side it happens to go up, on the right side it has to go up also. Or maybe it would be on the left side it's down, while on the right side it would be down also. So that's what it means if it has even multiplicity is on the same side of the x-axis. So notice how these are both above the x-axis and these are both below the x-axis. And just to mention again, we will go through some examples of these. So we have the wholes, we have zeros, vertical asymptotes, and the next one says horizontal or slant asymptotes. And that's what we're going to talk about now. This one has 3 different options, and this is about the degree of the numerator compared to the degree of the denominator. Now, just to recall, the degree is the number of if you look at the terms in the numerator and the terms in the denominator, the degree is the one with the highest amount of variables. So if you had, let's even go up here, the degree of this numerator here, the degree is 2 because the highest exponent there is 2. And then the degree of the denominator is 1 because there's an understood 1 there, and that's the highest degree of the denominator. So that's what we're talking about, degree. So there are 3 situations that we could have. The degree of the numerator could be less than the degree of the denominator. The degree of the numerator could equal the degree of the denominator. And the degree of the numerator could be greater than the degree of the denominator. So we have those 3 situations. In part C, in precalculus here, or in this lesson, we're only going to be talking about one situation there, and we'll get to that when we get there. So here's how it works. Part A, if the degree of the numerator is less than the degree of the denominator, well, that would be if we had y equals, the degree of the numerator is less, like x squared minus 4x plus 7, and the degree of the denominator, well, we want the degree of the numerator to be less. That would have to be x cubed or higher. And I'm just making up some arbitrary polynomials here, numerator and denominator. But that fits that situation, which means we would have a horizontal asymptote at y equals 0. So if we had, there's my graph, we would have a horizontal asymptote right on the x-axis. Now, these horizontal asymptotes, realize this is a little bit new to us. They can be crossed. You can cross over a horizontal asymptote, but the horizontal and slant asymptotes that we're talking about here deal with what happens at the far ends of our graph, kind of like end behavior when we talked about polynomials. The next part here, the degree of the numerator equals the degree of the denominator. Well, if they're equal to each other, you're going to have a horizontal asymptote again, but this time it's going to be at y equals, so it's going to be a horizontal line again, the leading coefficient of the numerator divided by the leading coefficient of the denominator. So, for example, if we had y equals 3x squared minus 7x plus 9 over 2x squared plus 5x, the degrees are the same. They're both 2. And so it fits that the degree of the numerator is equal to the degree of the denominator. So therefore, I should put an equal sign here. Therefore, there would be a horizontal asymptote at y equals 3 over 2, because we look at the leading coefficients. And then the last situation here is if the degree of the numerator is greater than the degree of the denominator. And for our purposes right now, it's only going to be 1 greater. So we're going to be looking at things like f of x, and we want this to be 1 greater. So maybe 3x to the 4th minus 2x squared plus 5 over 2x cubed minus 7. And so we see this as 1 greater. Therefore, we will have a slant asymptote. Slant means it's not horizontal or vertical, at y equals mx plus b. So it's going to be a line. Well, where does that line come from? It actually comes if we were to divide, do long division, if we were to divide this, we're doing an x cubed into an x to the 4th, we would get some mx plus b here. In fact, we also will have some remainder, which the remainder we don't really concern ourselves with because this is the line it gets closer and closer to, and this actually becomes a really small number that's insignificant, but that mx plus b, when we divide, that'll be the line of the slant asymptote. So the horizontal or slant asymptote is sometimes the trickier part of this, but it's not too bad once you do several examples and get used to it. Once you do all those things, once you find the holes, the zeros, the vertical asymptote, and horizontal or slant asymptote, notice you'll never have a horizontal and slant. There will only ever be one horizontal or one slant asymptote. Once you do all those things, sometimes we can find the y-intercept. To do that, you plug in 0 for x. Maybe some other helpful points. And then step 7, we actually graph it. And we'll have to talk through this during our examples. But we're going to determine where one branch of the function is. And these, so here's just a quick example of what a function might look like. It might look something like this. And this is just one sampling. So notice this is kind of in 3 different parts. I'm calling these 3 different parts branches. That's what I was referring to when I said branches. So the purple branch, the red one, and maybe we can put a green one in here. So we'll figure out one of those branches, maybe by choosing a point or something we know about the function. And then from that, we should be able to determine all the other branches using x-intercepts and their multiplicities, vertical asymptotes and their multiplicities, and the horizontal or slant asymptote. So that is the process or the strategy for graphing rational functions. And we'll, as we go through each example, we'll basically have this list up here and walk through each step.